Hello viewers, this is my second lecture on the topic of sensor transducer, where today I will discuss on the resistance temperature detector, which is one of the mostly used temperature sensor in the industries. So the resistance temperature detector is a resistive temperature transducer, where the temperature is measured in terms of change of resistance of the conductor. So how it works, let us see. So it comes under the electrical resistance thermometry. What is this? So basically, depending on the temperature, how the resistance of a conductor change, that is called the electrical resistance thermometer. And we all know that for the metal, if the temperature increases, then their resistance will also increase. And how this temperature is increasing, that measurement can be done if we can measure the resistance of that particular material. And the resistance is an electrical quantity. So therefore, using this transducer, we are able to convert the change in the temperature into a electrical output. So therefore, it is very much useful for the industrial applications. So resistance temperature detector commonly employs platinum or nickel resistance wire element whose resistance variation with temperature has a very high intrinsic accuracy. And they are available in many configurations, many sizes. Okay, so we will see how the different type, depending on the configuration, depending on the sizes, what are the different type of RTD that we will also discuss over here. And we also have the different material, that is we have discussed that platinum, and except platinum, the copper and nickel, these are also useful as the RTD. And here we can see the resistance temperature range. So that is, for the platinum, it can be used for measurement of temperature minus 190 degrees centigrade to 630.5 degrees centigrade. Similarly, for the copper, the range is minus 50 degrees centigrade to 250 degrees centigrade, and for the nickel, it is 200 degrees centigrade to 350 degrees centigrade. So, in these different ranges, we can use the different materials RTD, from where we can see that the platinum can be useful for the large range of the measurement. So here it comes that how the temperature, how depending on the temperature, how the resistance changes. So from this graph, we can see that this x-axis represents the temperature and the y-axis represents the resistance, and we can see it is a linear graph. Okay, so basically, if the temperature increases, then the resistance will also increase. So this thing is true for the platinum, nickel, copper, all the cases. The specific graph for the different material will be shown later. So here the RTD, it is having the, we can say that as the temperature increases and the resistance will also increase. So it is basically having a positive temperature coefficient of resistance. Okay. So these are the PTC type of transducer. Okay. So once the temperature, depending on the temperature, once the resistance changes, okay, so this change in resistance can be measured either by using some bridge circuit or by the normal, if we give a constant current to that particular resistance, then there will be a particular voltage drop across the resistance, and if the resistance changes, then the voltage drop will also change. So depending on that, that is from this voltage current ratio, we can also calculate what is the change in the resistance. So in this two more process, we can measure the how much change in the resistance is occurring. Okay, so the controller measures the resistance by passing a current through the RTD. Use a base resistance value. So this, what is the base resistance value? Base resistance value is basically, for example, the platinum value of 100 ohm at 0 degree centigrade. That is the at the ice point. Okay, so this is the base value of the resistance at 0 degree centigrade, 100 ohm. So that is why basically the platinum RTDs are mostly known as PT100. Okay, so PT100 is basically the platinum RTD where the resistance at 0 degree centigrade is 100 ohm. Okay. So next, here we can see what are the different types. So basically, there are basically wear-on type, thin film type, and kept-on insulated. So wear-on type is the mostly used RTD in the industrial application. But apart from that, for the if I want to measure the surface temperature of any particular plane surface, in that case, the thin film type of RTD is also useful. What is the thin film? It is basically there is a base material like this, and this base material can be plastic, paper, in that type of material, and on that, or Teflon, that can the type of material, and on that a thin film of conductor material is deposited. Okay, and the lead wax comes out from there. So this type of configuration is called the thin film configuration. And sometimes on this thin film configuration, the Kapton, it is a type of material which is insulating material, and its a layer is given on the top of this base material, so that the main RTD material remain protected from the external hazards or any mechanical deformations. Okay, so therefore these are the different types of RTD. Now let us see why the platinum is most preferable. So basically, we can see apart from the other properties, we can go for this particular graph first. So in this graph, we can see that for a different temperature range, we can see the graph for the platinum, copper, and the nickel. And we can see that in case of the nickel and the copper, though the sensitivity is high, that means the rate of change of the resistance is quite high with the change in the temperature, but this is having a linear range, maybe up to this temperature value, and for copper up to this temperature value, like this. But for the platinum, we can have, for a large range, we can have a linear characteristic of the output. Okay, so this linearity is very much required for the simple application of the RTD. So as the linearity of this graph is high for the higher range in case of the platinum, therefore platinum is mostly preferred as the RTD material. Now apart from this range, some other properties also makes the platinum suitable for making the RTD. That is, the platinum is quite stable, that is chemically inert, can be drawn to fine wares. Okay, a very thin diameter wares can be drawn using the platinum, and available in high purity. Highly pure platinum can be easily available. Okay, so these are the other properties that makes the platinum most useful for the RTD material. Now let us see how the temperature and resistance related mathematically. So basically, if we see the mathematical relationship between the resistance and temperature, it is described by using this particular equation. What is this? This is the R is equal to R0 into 1 plus alpha 1 t plus alpha 2 t square dot dot alpha n t to the power n. So what does it mean? Here the alpha 1, alpha 2, these are the coefficients. R is the resistance at T degree centigrade, and R0 is the resistance at 0 degree centigrade for that particular RTD. Okay, and we can see the overall equation is a non-linear one. Okay, so throughout the range of the operation, the RTDs are basically non-linear. But if we use for the small range, we can use this particular equation up to the first term, that is alpha 1 t, and if I use up to this, that is the R0 is equal to 1 plus alpha 1 t, this is basically a linear equation. Okay, so therefore for the while the very accurate, very highly accurate application is not there, in that case the equation, that is the RT is equal to R0 into 1 plus alpha t, that equation is enough to describe to calculate the resistance at T degree centigrade for the RTD. Okay. Now, what is the value of this alpha? So the alpha value basically depends upon the material, and like in case of the copper, the alpha is 0.00427 per degree centigrade. Okay. Similarly, for the different material, the alpha value will change. This is basically the coefficient of the resistance. So this graph is already described. Now, how the construction. So here we can see the construction of the wire wound type RTD, which is industrially used mostly. So in this construction, we can see that in between this portion, okay, this last type of thing we can see. This is the former made up of some mica. Mica is a insulating material. Okay, the insulator made former is there. On this former, the wire wound, that is the conducting wire, these are the conducting wires, those are wound on the mica former. Okay, and this structure is put inside a stainless steel well. Okay, that well is protecting the actual RTD material, because the RTD material is made up of very thin platinum wire. Okay, and that should be protected from the external industrial hazards. So therefore, this stainless steel well is there. Inside this well, the RTD material is kept, and to give proper heat exchange between this stainless steel wire and the RTD material, there are some ceramic powder present. So this ceramic powder helps for the exchanging of heat in between the external atmosphere and the RTD, and also it gives a proper bushing around the particular RTD and this in between the steel sheet, so that the particular RTD material is fixed rigidly inside the particular sheet. It will not be moving. Okay, so that is the how the main RTD is constructed, and these wires end part, that is the lead wire, are coming out from this direction. Okay, and from there we connect the lead to the signal conditioning circuit for measurement of the RTD resistance. Okay, now we will see how the RTD resistance is being measured. So that is the signal conditioning of the RTD. So in case of the signal conditioning of the RTD, it is basically a resistance which is changing due to change in the temperature. So we need to measure the resistance over here, and we all know that the Wheatstone bridge circuit is one of the useful circuit for the measurement of the resistance. So therefore, the Wheatstone bridge circuit is used for measurement of the RTD resistance also. And apart from that, as we have already told, using the normal volt ampere method, we can also measure the resistance of the RTD. But normally, the bridge circuit is preferred. So now, what is the problem in the RTD resistance measurement? Let us see that. So there is a main problem. We can see it using this particular diagram. So basically, what is there? You see, if I consider this is my RTD. Okay, so RTD is having 100 ohm at 0 degree centigrade. That is for a platinum RTD. We have told this is the standard. That is, it is having 100 ohm at 0 degree centigrade. Now, this RTD will be connected to the bridge circuit using the lead wire, because this lead wire are required, because normally this RTD will be present in the process. Okay, maybe inside a tank, inside the boiler, where we want to measure the temperature. But the signal conditioning circuit will be present in the control room side. So from this plant location to the control room, there is a distance. There may be a distance of few meters to 1 or 2 kilometers also. So in that long distance, the wire which will be connecting the field RTD with the signal conditioning present in the control room, that is the lead wire. Okay, so this long distance of the lead wire will have a significant value of the resistance. This value cannot be neglected. Why this value cannot be neglected? Say suppose for a wire of any several meters length, we can consider the resistance of that particular wire is only 5 ohm. Okay, if we use normal wires, lead wires, that values are very less. That resistance values are very less. Here we consider it as to be suppose 5 ohm, which is quite less here. Now for the two wires, the total resistance which is coming, it is the 10 ohm. Okay. Now you see, for the standard temperature coefficient, that the temperature coefficient alpha is basically like this, like the 0.00385. Okay, so if alpha value is this, what is indicating? Indicating that for 100 ohm where 0.385 ohm temperature ohm resistance change occurs for every 1 degree centigrade change in the temperature. So for every 1 degree centigrade change of the temperature, the resistance change is like this. Okay. Now alpha is equal to the average slope from 0 to 100 degree centigrade. So let us say that if I consider that particular graph, that is this side it was the resistance, the temperature, and this side it was the resistance, and so for the 0 degree to 100 degree, suppose, okay, the so 100 ohm, so it graph will change something like this. Okay, so what is the average slope? So average slope means like this. So it is the basically the this gap is basically the del T, and this gap is basically the delta R. So the average slope means this del R del T, like this. So this is the uh, scenario. So you can see that alpha basically indicates this del R by del T. Okay. So for every 1 degree centigrade rise in the temperature, how much the resistance is changing. So as per this, if this is the alpha value, so for a 10 ohm lead wire, that implies 10 by 0.385, that is 26 degree centigrade temperature. Okay, so when I am going to measure the resistance of this particular RTD, okay, so with that this two 5 ohm will be added, and by addition of this to 5 ohm, that will imply that actually like in the output side, in the control room, we will pretend that the 26 degree centigrade temperature has been changed. Okay, but actually this temperature has not changed. Okay, so this create a significant error in the measurement. Okay, so therefore we have to be aware about this kind of error. So this error which is incorporated due to this lead wire, that is called the lead wire error or the lead wire effect in case of the RTD measurement. Okay, so therefore we have to eliminate this lead wire effect. So how to eliminate this lead wire effect? So to eliminate this lead wire effect, we are going to use two techniques. Okay, one is called the 3-wire technique, and another one is called the 4-wire technique. So let us now see what are the 3-wire and 4-wire RTD signal conditioning circuit. So first is the this is the 3-wire RTD. So how it is working? This is the supply voltage. Say this is the R1, R2, R3, which is a variable resistance, and R4 is basically the RTD, and these are the lead wires A, B, and C. Okay. So in this particular circuit, here, though we know that RTD is a simple resistance, but here the resistance is having three terminals. Okay, from one terminal, basically two lead wires are coming out. Okay, and these two lead wires are connected in the bridge circuit like this. Normally, if it was a two-wire RTD, then this B part, this B wire will not be present, and this point will be connected over here at this point. Okay, but here, as it is the three-wire, the connection is something like this. So in this particular connection, when the bridge is in the balanced condition, we all know that the equation for the balance is something like that: R1 by R2 equals to R3 by, if I consider this to be the fourth arm, then it will be like the R4. Okay. Now in this case, the R4 is basically the RTD. But here, not only the RTD, with that the lead wires are also connected. So the lead wire distance will also be considered over here. Okay. So how to do that? So basically, and also we know that if I can make that R1 and R2 to be the equal, okay, then the change in the R3 is actually reflecting what is the change in the R4. So we cannot go in the field and measure that what is the change in the R4 has been occurred in the RTD. So what we can do, we can have a potentiometer in place of the R3, and if the bridge is unbalanced due to change in the resistance of the RTD, we will rotate the potentiometer's knob, which is being rotated on a graduated scale. Okay, and how much rotation, after how much rotation the bridge is again balanced, that indicates that how much resistance change have been occurred in the particular RTD resistance. Okay, so from there we can manually calculate that what is the change in the resistance of the RTD. Now, apart from that, we can also get the change in the resistance of the R3 by using the normal volt ampere technique also. So here, what we need to make is that the R3 should be equals to the RTD resistance. Okay, but if I consider this particular equation for this scenario, what is actually happening? Actually, over here it is happening like that the R1 by R2 is equal to, so R3 is over here nothing but the R3 plus, so R3 plus the lead wire A plus the lead wire B by R4. What will be the R4? R4 will be basically, it is the lead wire B plus the RTD resistance plus the lead wire C. Okay, so now as the R1 and R2 are two standard resistances, so we can make let then we can have the R3 equals to, so B cancels from each side, so R3 plus A equals to RTD plus B. Okay, so this equation we can get over here. So here we can see that R3 plus A equals to RTD plus B. Now in the industry, as the lead wire is coming for the same length, that is from the RTD to the signal conditioning circuit, the length of A and B will be same. So in that case, the value of the A and B should be same for actual cases. So therefore, in that case, we can say that the R3 is equals to the RTD. So therefore, if I can measure the value of the R3, that is basically the measurement of the RTD resistance. That how much change in the resistance has been occurred. Okay. So using this three-wire, this is how we can have the we can now eliminate the effect of the lead wire resistance. Okay, as the lead wire is being added in both the sides of the equation. Okay, now the thing is that this may not happen in all cases because this A and B may be made up of the two different wires. That is basically two different wires, and therefore their thickness may also change, or their somewhere the material may also change. So therefore, the value of A and B may not be same in some cases. So in that particular aspect, we have to go for the four-wire RTD. Okay. So how the four-wire RTD works? Let us see. So in case of the four-wire RTD, there will be another lead wire coming from the other terminal, and that is basically the A, B, C, and this one is D. Okay. So in this case, the circuit is something like this. Okay. So in this case, what will happen? Basically, the R1 and R2 we can make equal. So therefore, we can say that the R3 plus A plus B equals to B plus RTD plus B plus RTD plus D. Okay, and now the B can be cancelled, so we can have R3 plus A minus B equals to RTD. Okay, so let us have consider this is the configuration A. So this is our configuration A. Okay. Similarly, we will have another configuration, say something like this. So in this case, the lower one will be connected over here, this voltmeter, and the upper side will be connected to the downward side, and the downward side will be connected. That is the B will be connected to the this side, and the where A that will be connected to the lower side, and in the meter the C will be connected. So A, B and C, in the meter the C will be connected. Okay, so here it comes again R1, this one is R2, this one is your R3, which is the variable resistance, and this is the RTD. So the change is that here the A was connected to the R3 and the D was connected to the end of the R2, but here it is reverse, that is the D is connected to the end of the R3 and the A is connected to the end of the R2, like this, and instead of the B was connected to the voltmeter, here the C is connected to the voltmeter, not the B is kept open. Okay, so in this particular configuration the balancing equation will be something like that, that is the R3, it will be added with the D and it will be added with the C. Okay, so R3 plus D plus C is equal to it will be equal to now R4, it will be basically the C plus the RTD plus the A. So C starting from the voltmeter, C plus RTD plus RTD, okay, plus the A. Through the A it is ending, the circuit is ending. So here also we can have that C cancels. So R3 is equal to RTD plus A minus B. So we can have over here, that is the R3 is equals to RTD minus A plus D, sorry, plus D. Now if we add these two equations, so we can have, suppose this is our equation 1, this is our equation 2. So if we add equation 1 and 2, so we will have 2 R3 equals to this one plus that one. So here we are having RTD minus A plus D. Here we are having RTD plus A minus D. So this A and D cancels from both sides. So R2 R3 is equals to basically the 2 R T D. Okay. So here from we can have that the measurement of R3 is equals to the 2 into RTD. So we can have the measurement of R3 once, say suppose we can get one measurement as R3A and another measurement as R3B. Okay, so in that case it will become R3A R3B. Okay, so in that case the RTD value will be basically the average of these two readings. RTD value will be equals to the R3A plus R3B by 2. So this is how here we can get that we have to take two measurements of the resistances and take the average of that. Then we will have the value of the RTD, which is totally free from the effect of the ABCD any kind of lead value. Okay, so this is useful for the very highly accurate measurements, and this can be used only for the laboratory purpose. It cannot be used for the industrial applications. Okay, so this is how here we have come to the end of the discussion about the RTD. So here we can see that the RTD is a very much useful uh, sensor for the temperature measurement in the industry, as well as any other kind of applications like the household temperature measurement systems also. We can use this kind of RTD transducers, and as they are simply made up of some conducting wires resistances, their construction is very simple and they are very low cost budget in construction, and they can be useful for the any kind of like the in case of household or the industrial application as well. Okay, so that's all about the RTD, that is a resistance temperature detector. Thank you.